For this lesson, we'll be focusing on transducers. Transducers are devices used to convert a physical parameter into an electronic signal. These are also known as sensors. Now, what is meant by a physical parameter? It could be anything such as temperature, force, flow, or light intensity. Now, when referring to transducers or sensors, there's an endless supply inventory of the amount of transducers and sensors that are out in the real world. Unfortunately, it's very difficult to keep up with all the new latest and greatest types out in the field. However, we're just going to go over a few of the most common types. We're going to go over RTDs, strain gauges, and encoders for this particular lesson. Now, as stated in the previous slide, it is very difficult to keep you up to speed on the latest and greatest transducers in the world. However, it is very common to come across transducers new and old with the similar signal conditioning. Majority of transducers out there, and I'm referring to the analog ones, produce an output of 4 to 20 milliamps or a DC voltage between 0 to 5 volts. And again, I'm referring to analog signals, not necessarily DC, because most DC signals will produce either 5 volts to 0 volts, 0 to 12 volts, or 0 to 24, depending on what type of transducer you buy. Now, National Instruments provided a nice, pretty illustration there, where it actually has a 4 to 20 milliamp transducer with a power supply in line with it, and it's outputting to a DAC unit. And that's actually very common out in the field. Now, unfortunately, what you don't see is within that transducer, sometimes there's internal components that produce that 4 to 20 milliamps or this output voltage. Because with its raw material, it can't do it alone. It needs these extra components. And some of these extra components mimic a Wheatstone bridge. And we have a circuit below with a Wheatstone bridge and its associated equations. And we'll go over one of these example problems later on. Now, when I refer to transducers using their raw material, I'm referring to active transducers. These are sensors that actually have a self-generating output without any additional power source. For example, in the illustration on the left, that is an actual picture of a thermocouple. And a thermocouple is basically two wires or two different metals being twisted together. And as heat is being applied to these two metals, it actually creates a voltage. It's not a lot of current, but it's enough voltage that way it can vary based on how much heat is being applied to these two metals. In an illustration on my right, I have a piezoelectric transducer. So when you think of active transducers, think of a piezoelectric transducer. And the second type of transducers we have, or class, we have a passive transducer, which is probably the most common, the one you're going to come across out in the field. These are the types that require an application of a power source to actually function. Now we can start digging into the weeds. Now we can start going over specific transducers. The first one I want to go over is resistance temperature detectors, also known as RTDs. And they're a device used to relate the change in resistance to the change in temperature. So when you actually have these particular components in an environment, anytime temperature goes up and down, the resistance of the component would go up and down. And to calculate the resistance, we have an equation provided to the left. Now, most of these RTDs are made out of platinum, which means you'd have a temperature coefficient of 0.00367. Now, this can actually vary depending on which book you have. Some of them have 368, 388, but just give you a heads up, this is just one I used out of one of my textbooks. Regardless of which one you use, your number should be about the same regardless. Now, these RTD values, when it refers to the reference value, that's the actual rated value typically for that RTD. And the typical values that you'll see on some of these data sheets could be 100 ohms, 200 ohms, 400, and so on. Now, in wiring these RTDs, there's typically three configurations you'll come across: a 2-wire, 3-wire, and 4-wire configuration. A 2-wire is the simplest out of all of them. It's basically two leads that go straight to the RTD. However, when you have those two leads, it doesn't really tell you the length or the resistance of the cable you're hooking to the RTD. So if you're going several feet away to 100 meters away, you're going to have some resistance within the cable that's going to be unknown to you. That's where the 3-wire configuration comes in. Two leads connect to the RTD, and the third lead connects to one of the same leads. So if you see in the illustration, you're connected to your RTD, but you have two red leads. What this allows you to do is measure between those leads and obtain the actual resistance of that cable. So you can actually negate it when you do your calculations for resistance. This provides actually a more accurate reading of your RTD. And it's actually a very common method. Now, the most accurate but most complex method is your 4-wire configuration. One set of leads supplies a constant current, and the other measures the actual voltage drop. So this one, even though it actually has more wiring involved, it's also the most accurate. The next transducer we'll go over is the strain gauge. The strain gauge is a device whose electrical resistance varies on the proportion to the amount of strain on the device. So on the illustration to the right, you'll see an actual flat piece of metal, and it has two leads coming out the end. Well, as this metal or this mesh is being bowed or compressed, that will affect the resistance values. So you'll usually see these like among load cells or anything you want to calculate any particular strain or stress. Now, when you see data sheets for these strain gauges, you'll see a factor called gauge factor. And this gauge factor is the ratio in a fractional change in electrical resistance to fractional change in length. Now, this may be a little confusing, but it's typically 2 on a data sheet. And we'll go over one of these problems later on. Now, this is where I save the best for last. The last transducer we're going to go over is known as a digital output displacement transducer, which is most commonly known to us as encoders. And what makes these interesting, encoders can measure any type of distance or displacement, and it could be either shaft angular or linear displacement, and it gives it to you in a digital readout, usually in an increment readout. Now with these encoders, there's usually two different types. There's photoelectric and magnetic. Photoelectric consists of a disc with a coded pattern, and then it has a sensor with a light source going through it. So as this pattern rotates, the light's going to appear to shut on and off, and the sensor is going to actually tell how the encoder is moving in which direction. Magnetic's very similar, however, it just consists of a magnetic reading head and a partly non-magnetic coded pattern. Again, they're both very similar, they just operate or have different components internally. So let's jump into a little more detail on this encoder output. For this particular one, we're going to go over rotary displacement transducers, and again, these are encoders, but these are incremental encoders, which provide a 1 or 0 pattern in the form of counts. So in the picture at the top left, you'll see an actual encoder, and as it spins, that pattern will turn with it and provide you a square wave on its output. Now, typically with these encoders, it usually has minimum 2 phases, an A phase and a B phase. Some of them have C and D, just depending on how expensive or how extravagant you want to go. And here's the reason. Well, when you have these 2 phases, it can actually help you determine which direction the encoder is going, because sometimes you want to be able to tell if it's going forwards or backwards. Now, when you look on the data sheet for these encoders, they provide an output in pulses per revolution per channel. Again, this output phase, that's considered to be a channel. So anytime you have an encoder with a heavy amount of pulses per revolution, that's how accurate that encoder is. So if you can barely turn it, it's going to go through several pulses and let you know how many turns or how many revolutions you have done on that particular encoder. Now, absolute encoders have a coded pattern which outputs a digital word such as a binary or a gray code. Typically, it's gray code. And the reason they use gray codes on some of these encoders is because if one is starting to break down or skip, it's very easy to determine on a gray scale or a gray code, because a gray code only changes 1 bit at a time. So as it's rotating or incrementing, if it changes 2 bits at once, you know there's something wrong with that encoder. Right, let's jump right into our first example. For this one, we have a 3-wire platinum RTD and it is installed in a clean room. Before connecting the RTD to a temperature module, the resistance values were measured. Determine the actual ambient temperature of the clean room. All right, so right now we have our RTD, and it looks like a 3-wire RTD, and it looks like we have resistance values measured before it was actually connected. Now right here between L1 and L2 is the total resistance, and that includes the cable with the RTD. And then between L2 and L3 is our lead length resistances, and that's just of the cable itself. That's kind of the purpose of why they do 3 wires. It gives you a chance to measure just the cable, not counting the RTD. So if you had a 100-meter cable, you'd be able to determine the resistance of that cable. And that's important because it gives you a chance to go ahead and omit it or remove it from your total resistance. And some temperature modules out there actually have it so you can input this lead length resistance so that it can automatically omit it from the actual total resistance. So the first thing we're going to do is we're going to go ahead and remove this resistance out of our total resistance. So what we're going to do is we're going to say 156.51 ohms, because that includes the resistance of the cable, the RTD, and then the cable returning. And then we're going to minus 1.46 ohms. And that's a simple plug and chug. That's going to give us an answer of 155.05 ohms. So by doing that, we determined the resistance of the RTD itself, nothing else. And that's what we want. That gives us an accurate value of our RTD. Now that we were able to omit the cable, now we can probably move on and start determining what our variables are. So let's go over what we know. So RT, and that's going to be the current RTD resistance. Well, we just determined that, so it's 155.05 ohms. We have our reference resistance, and that's R sub O. Now, anytime you see 100 ohm RTD or 300 ohm, that's referring to your reference resistance. So right there, that's an easy one. That's 100 ohms. Next, we have our alpha, which in this case, that's our temperature coefficient. Now, I already said it was platinum, so that one I went ahead and that's a given right there. Again, if you have to look up other materials, such as different metals, such as iron or copper, you can look in some of your textbooks or some of your PE references, and they'll give you these actual temperature coefficients. But for platinum, I just went ahead and pulled out one of my references and pulled out this number for you. So it's 0.00367, and that's Celsius, and that's going to be inverted. Okay, next we have our current temperature. Now this is what we're going to try to determine. We're trying to determine our ambient temperature. And this is very important. This is our reference temperature. Now right now, we didn't state anything about reference temperature. It wasn't even mentioned in the PowerPoints. Reference temperature, anytime you see 100 ohm RTD, that's referring to it's 100 ohms at 0 degrees Celsius. Your reference temperature for this one is going to be 0 degrees Celsius. Usually if it's not stated in a question or on a data sheet, you're going to see 0 degrees. So just keep that in mind. If it's not stated, just think of it as 0 degrees Celsius, and it's going to be at 100 ohms. So in other words, as the resistance goes up, your temperature should be going up. All right, now let's see if we can start plug and chugging some of these variables in this equation right here, and we'll start working it down. So we're going to say RT, I'll say 155.05, that's ohms, equals your reference, which is 100 ohms. Then we have a bracket, 1 plus, and this is going to be our alpha, which is going to be 0.00367, and that's going to be Celsius inverted, parentheses, and I want T minus 0 degrees Celsius. And let's see if I can fit all that in there. Now let's go ahead and start doing our algebra. Let me go ahead and divide both sides by 100 ohms. Always go for the low-hanging fruit first. And that's going to give me 1.5505. That's going to equal, it's going to be 1 plus, and again, our alpha again, 367 degrees Celsius inverted, and temperature minus 0 degrees Celsius. Now I can also just do another easy one, minus 1 from both sides. So it's going to be 0.5505. I know a lot of this is really repetitive, me rewriting this, but it's part of doing the steps process. And temperature minus 0 degrees Celsius. All right. Now, just to make it easy on myself, I want to go ahead and multiply our alpha times T and then times 0, so we can get rid of these parentheses. Good news is, by doing that, alpha times 0 is pretty much 0, so that one's going to be easy. So it's going to be 0.55.05 equals, and it's going to be 0.00367 degrees Celsius inverted times T. Pretty much after that, since I'm trying to find T, I just go ahead and divide both sides by our alpha, which is 0.00367 degrees Celsius inverted. And again, same thing. It's very tedious drawing this all out. Since I ran out of room, I want to go ahead and move all this up real quick. All right, and if I plug and chug this right and I calculate right here, it's going to give me T equals 150 degrees Celsius, which is actually pretty warm. If you actually convert this to Fahrenheit, it's going to be 302 degrees Fahrenheit, which means there's something wrong with that RTD, or that's a very, very hot clean room, or likely the technician who installed the RTD put it right next to an oven. Just right here alone, you can automatically assume, and once you hook this up to a temperature module, if you see 150 degrees Celsius, it's not going to be the temperature module, it's going to be your RTD that's giving you that value. So it might actually help you in the troubleshooting phase. But Right there, that's our final ambient temperature. All right, let's go and jump to our next example. All right, for our next example here, we have a 1.5K strain gauge and it is used to measure the weight on a scale. To ensure accuracy, the strain gauge is connected to a Wheatstone bridge with R1, R2, and R3 also equaling 1.5K ohms. So that's good news. Based on the strain gauge datasheet, the gauge factor is 2.1. Determine the strain and resistance if the Wheatstone bridge output indicated 417 microvolts. All right, so we have a little bit of information to work with here. So we know R1, R2, and R3 all equal 1.5K. And we know V out, and I'll go ahead and write it right here, equals 117 microvolts. And we want to determine for this strain gauge, we want to determine its resistance and we want to determine its strain. So that's two things we have to find out. Well, the good news is it looks like we have enough variables here to actually input a majority of them in this equation right here. Because we have our V out, we have all of our R1s, we have our R2s and R3s. We don't have, this is going to be considered R4 for the sake of this equation, and that's all we have to look for. We just have to use a little bit of algebra and extract out of that equation. Now keep in mind, this Wheatstone bridge came out of your FE reference handbook. Some of the Wheatstone bridges in other textbooks are actually arranged differently. Sometimes R3 is on the left, R2 is on the right, sometimes your negative and positives are swapped. If that's the case, this equation is not going to work the same. It's going to be different. So your equation must match the circuit. If it does not, you're going to have to rearrange R1 and R2 accordingly to actually be able to plug and chug in this equation. Just keep that in mind. I had 3 PE references that all the Wheatstone bridges were arranged differently, what they consider R1, R2, R3, and R4. So just keep that in mind. All right, with that being said, now we can get moving and go ahead and plug and chug in this equation right here. So 417 microvolts equals, now this is going to be considered R4 for the sake of argument, because in the PowerPoint, this spot right here was reserved for R4. So we're going to use that same one. So we're going to say, and this is going to be our numerator, R4 times R1, which is 1.5K, minus R3, 1.5K, times R2, 1.5K. And we'll close those parentheses. And see if we can do a denominator. R4 again, unknown, plus R3, 1.5K. And that's going to also be another parentheses. So 1.5K plus 1.5K. And forgive my handwriting as usual. And that's going to be times. And this is going to be our input voltage, which is 5 volts. Okay. Now let's see if we can clean this up a little bit. So we have 1.5K R4 minus, and then 1.5 kilo times 1.5 kilo is going to give us 2.25 mega. And I'll just make that in parentheses. Over. And then we have R4 plus 1.5K. And then we have 1.5 plus 1.5, that's easy. It's going to be 3,000. And then times 5 volts. Okay, so far so good. What I'll go ahead and do is I'll go ahead and write this guy up here. Maybe we can start working our way down. All right, I went ahead and erased the bottom down there so that way we can keep moving and that way I have a little more space. All right, now the next thing I want to do is I want to see if I can extract this 1.5 kilo from this actual equation or this numerator up top. Because if I do that, it's actually going to clean it up so I can get rid of this 3,000. I'll show you what I mean. So 417 microvolts equals, and we'll say 1,500 times R4 minus, now if you divide 2.25 million by 1,500, it's going to drop you right back down to 1,500. And then we have our denominator. And I'm going to put our 3,000 right here instead, just to make it easy for us to follow. And then R4 plus 1,500. And then we have times 5 volts. So that was actually pretty easy to follow. And what I'm going to do is I'm going to just go ahead and get rid of 1,500 divided by 3,000. Well, you can do that in your head. That's going to be half. So you're going to have 417 microvolts equals 0.5. And I'm going to just write these same ones again. So bear with me. and please excuse the handwriting, and then times 5 volts. So what I can do is I'm going to have multiply 0.5 times 5 volts, and that's going to give us 2.5 volts. So I can go ahead and say 417 microvolts again equals 2.5 volts, and then write our same equation again. Very tedious, but I just want to go through the steps, that way you could follow along without missing anything. All right, now what I can go ahead and do is I can divide both sides by 2.5 volts, so I can get rid of this guy. So I'm going to divide 2.5 volts and then 2.5 volts. I'll tell you what, I'll move it over here real quick. 0.000168. That's going to equal R4 minus 1500 over R4 plus 1500. I want to go ahead and see if I can erase this so we can keep on moving. So what I'll go ahead and do is I'll go ahead and multiply our denominator times 0.0001668, and I'll go ahead and move it to that side of the equation. So let me go ahead and do that up here. So I'm going to say R4, and I'll tell you what, I'll put in engineering terms, is 166.8, and this is going to be micro, and then plus 1500 times that same thing. It's going to give us 0.2502, and then it's going to equal R4 minus 1500. So far we're doing pretty good. All right, next I want to go ahead and add 1500 to both sides. Make it easy on me. And I'm going to go ahead and subtract the R4 from this side. So basically I want to put the R4s on one side, and then I put our raw values on the left side. So it's going to look something like this. It's going to say 1500.2502, because all I did was add 1500 to 0.2502, and it's going to equal, and I'm going to take R4, and it's going to be minus 166.8 micro. R4 of 0.9998332. I know it's a very odd and long number, but we'll get through it. And then we go ahead and divide both sides by 0.998332. Tedious, I know. All right, and that's going to give us a final R4 of 1500.500483. So that is going to be our resistance of our strain gauge. So right here I'm going to say our resistance for our strain gauge, we'll say R of G, is going to be 1500.500483. Now, in case you haven't noticed, look how small of a resistance value change that is. It didn't take much, and you have a slight voltage here. Because if this was 1500 on the dot, this would be 0 volts. That means you have a balance. But since this has a slight off balance compared to R2, R3, and R1, it actually gave us a voltage on our output. All right, now let me go over the easy way we could have done this. So I'll tell you what, let me go ahead and clean all this up. I'll go ahead and keep this answer right here. So anytime they refer to R, they're referring to the Wheatstone bridge. What is the balance? What is each resistor supposed to actually weigh for R? So it's referring to the 1500, because if every single one of these were 1500, your output voltage would be 0. So right now, if they're referring to the difference, they're referring to the difference of your actual strain gauge, and whatever that difference is from the 1500, that's the value right here. So here's what I mean. For the difference of resistance, it's going to be whatever your resistance value for your Wheatstone bridge is going to be. So it's going to be 1500 in this case, minus whatever change there is. So in this change, it's going to be 1500.500483. And of course, when you refer to difference, you refer to the absolute values, which means your resistance difference is going to be 0.500483. Okay, that's your difference in resistance. And then R is obviously your 1500, and then the rest of it we can just actually find out. So let's just say we didn't know this value at all. Let's just say we wouldn't go through this big long equation. it's going to look something like this. It's going to be V out, which is 417 microvolts, equals, and we don't know the difference yet. We know what the R is. We know it's 1500, because when it's balanced, every resistor is 1500, and then times our Vn, which is 5 volts. Doing a little bit of math here. Difference in resistance, and we'll leave the same. 4 times 1500, that's pretty easy, that's 6000, and then times 5 volts. And if I multiply 6000 times 417 microvolts, so just multiply times there, it's going to give me an answer of 2.502 equals difference in resistance times 5 volts. And if I divide both sides by 5 volts, it's going to give me a difference in resistance. I'll try to make that look like a delta of 0.5004. So that's a good sign, because right there, that looks like our difference. Now again, the reason it's about is because see how accurate I was able to go with using the big equation? So just keep that in mind. It's not perfect, but it's pretty close. Well, so now that I have the difference of resistance, now I can easily find my strain. And by doing that, I can use this equation right here. I'll tell you what, I'll see if I can finish it off down here. Now our gauge factor, which is right here, it's also considered K, is 2.1. And this is usually given by most of your data sheets. That's not something that you have to usually find out. Okay, that's going to equal. And then I have my difference in resistance. So we're going to say 0.500483. And this is divided by R, again, 1500 if it was balanced, and then divided by your strain. Well, we don't know what the strain is, that's what we want to find, so all I'm going to do is a little bit of algebra and swap those two around. So in other words, my strain is going to equal, and I'll just go ahead and do the math for those two. A very small number, this is not usually a big number. So this is just get your feet wet with a little bit of Wheatstone bridge, as well as how to calculate a strain gauge. All right, let's do one last problem. All right, let's jump right into our last example. We have an encoder that is attached to a shaft of conveyor belt. According to the data sheet, the encoder increments 1200 pulses per revolution. If the encoder outputs a square wave of 900 hertz, how fast is the encoder shaft turning in RPMs? All right, so this is a little bit of a tricky one, but we can start working it down. Let's write down what we know. First, we know we outputs a square wave of 900 hertz. 900 hertz equals 900 pulses per second. Okay, that's what we know, because if you remember, hertz is 1 over seconds. So basically, 900 hertz is 900 pulses per second. Okay, so far so good. And the accuracy of this encoder is 1200 pulses. So in this case, the encoder itself is 1200 pulses per revolution. All right. Now we want to use this information and determine how many pulses we're getting per revolution. That's what we want to determine. Well, if we divide 900 by the 1200 equation here, it can actually cancel out our pulses and we can get revolutions per second. Here's what I mean. So we're going to say 900 pulses per second divided by 1200 pulses, and that's per revolution. So remember, in the old days, anytime you divide a fraction, all you have to do is multiply it and swap the denominator and the numerator. So in other words, it's going to look like this. It's going to be 900 pulses per second, and then multiply. Now, since your 1200 is on the numerator, we're going to switch the denominator and swap these two around. So it's going to be revolutions, and then we're going to have 1200 pulses right here. So that was just a very simple method. Well, when you do that, and you go ahead and multiply these together, you're going to have, so you're going to have something that looks like this. You're going to have 900 pulses times your revolutions, and then divided by 1200, and this is pulses, that's per second. Well, the good news is this unit automatically cancels out, and you just go ahead and divide 900 by 1200. And that's going to give you 0.75, and we'll keep the revolutions because nothing canceled that out yet, by seconds. So the good news is we're able to come up with how many revolutions per second we have. And we want to determine how many revolutions per minute we have. Well, all we have to do is to convert revolutions per second to revolutions per minute. All you have to do is go ahead and multiply 60 seconds and 1 minute. So what this does is you go ahead and multiply all this together and the seconds will actually cancel out, which means 60 times 75 is going to give you 45, and that's going to be revolutions divided by, and this is going to be, seconds will cancel out, and this is going to be per 1 minute. So which means you're going to have 45 revolutions per minute. So the answer for this one's going to be 45 RPM. Now, just to give you an idea of how accurate this encoder was, if you want to determine the resolution of this encoder, it would be 360 degrees divided by how many pulses per revolution it has, because a revolution is 360 degrees. So that means you're going to have 1200 pulses for 360 degrees, which means you're going to have a 0.3 degree per pulse. That's pretty amazing. That means for every 0.3 degrees this turns, this encoder is going to know it. You're going to have 1 pulse. So every time, and that's another 0.3, and so on and so on. So that's just give you a heads up. If you want to determine the resolution, that's how. So hopefully this is enough information to get your feet wet. If you have any questions, feel free to let me know, and I hope you all have a good day.